Hey, welcome back. Hopefully you're not too overwhelmed from looking at 4 different ways to solve quadratic equations yesterday. Today we're going to take a closer look at just the solution. So, we saw the variety of solutions that we could have when we solve a quadratic yesterday, but I want you to really understand why we get such a variety. Now, we saw a snapshot of it, but the variety of solutions really happens because of one distinct part in the solving process. Now, I put 4 quadratic equations here and I solved them all using the quadratic formula. Not that that's the way that has to be used, but it's so that we can compare and see exactly where the differentiation is happening within the solutions, okay? So if we look at the first one, and if we were in class I would have probably made you do this work, but just save time here. The first one is actually a factorable equation, right? If we're looking at this, there are factors in -4 that make 3. It could factor into x plus 4 and x minus 1, and solutions of -4 and 1 then make sense, right? But if we just factored, then we wouldn't see what I want you to see in this set of notes. So we put this into the quadratic formula. And what happens in the quadratic formula here is a little different from what happens in all of the others, right? And if we look at what happens here in the second and the third, we're stuck with the radical. Now we end up with these nice solutions here because under the radical we ended up with a perfect square. So that perfect square was something we could square root, and then these two numbers became numbers that we could actually combine, okay? And I think we might have seen that exact example in the notes yesterday. So here we end up with 2 real solutions that happen to be rational, 2 real and rational solutions, and that happens because we ended up with this nice number under the square root. Now if we look at the next one, we end up with a 21 under the square root. So these are still real solutions, right? There's no negative under the radical to make them imaginary, but these 2 real solutions are going to be irrational because we can't take the square root of 21 exactly. It would be some non-repeating, non-terminating decimal. So here we get 2 real solutions, but these real solutions are irrational solutions. Okay, now if we look at the third one, we end up with a -80 underneath the radical. And that negative, although we could simplify the 80, that negative being under there comes out as an I, and that gives us still 2 solutions, but because it's imaginary here now, when we put the imaginary and the real together, we end up with these 2 complex, and really if you just wanted to call them imaginary, I'd be okay with that, 2 complex or imaginary solutions. And then the last one, what happens underneath the radical? Well, if we end up with a 0 underneath the radical, the square root of 0 is 0, which means that part of it just goes away. So we're not adding and subtracting anything, which means we end up with just 1 solution here. So 1 real and rational solution. Okay, so those are the 4 options that we've talked about. Now, what I want you to understand is these things are based solely off of the part that's underneath the radical. Right? It didn't really matter what was happening before the plus or the minus or on the bottom of the fraction. It's just that part under the radical that's going to dictate how our solutions end up. And that part that's underneath the radical, we call it the discriminant because it discriminates in the types of answers that we're going to get. So we saw 4 possibilities for solutions for quadratics, all based on what we call the discriminant. Discriminant, okay? That discriminant, which we're going to say is, again, the part underneath the radical in our quadratic formula, that's b squared minus 4ac, not the actual square root part, just the part underneath, just the radicand, okay? So that discriminant comes from our quadratic formula. So what you might be asked to do is look at a quadratic equation and not tell me what the solutions are, just tell me what the solutions would look like. So maybe I give you this quadratic equation and I don't say solve it, I just say, hey, what kind of solutions are going to have? Is it going to be 2 irrational solutions, is it going to be 1 rational solution, in which case you wouldn't have to go through all of the solving process to get the answers to see. If you just did the part under the radical, you're going to know, okay? So, what the heck? Sorry, my eraser is still on, and I erased some of my work over here. Okay, so what we have is, oh, I erased this too, son of a gun. Sorry guys, I'm going a little stir crazy in my house here, and talking to myself, it's not fun. And I talk to my kids here and my husband, but I don't think they listen, so I really feel like I'm talking to myself all day. Okay, so if your discriminant is a positive perfect square, that's what happened in this first box. So positive perfect square, that's what happened here. Okay, if we got, let me not highlight it there. That's what happened right here. If we get a positive perfect square underneath our radical, like a 25 or a 36 or a 49 or something we can square root, then what's going to happen is we're going to have two rational solutions. They will be real and rational solutions. Now, if the number we get under the square root is positive, but it's not a perfect square, if it's positive but not a perfect square, like 21, right? 21 is a positive number, but it's not a perfect square. You're still going to get real solutions, but they're going to be irrational. So that's going to cause two irrational solutions. Now, if you get a negative number under the square root, negative, it doesn't matter if it's a perfect square or not. So it could be a negative 80, it could be a negative 25. As long as there's a negative under the radical, it's going to create those complex or imaginary solutions. So anything that's negative is going to make that imaginary aspect. So it's two complex or imaginary solutions. And then the last option is, well, maybe we get a 0 underneath the radical. So if our discriminant is 0, like it was here, then that whole radical part goes away, and instead of the typical two solutions, you only end up with one solution. Now let me back up to that for a second. So here we get one rational solution. Actually, we'll come back to that. Why do we have one solution there versus two and all the others? So we'll come back to that in a little bit, okay? So you could be asked, like in these situations, to determine the number and types of solutions. So you don't have to go through all the solving process to know what the solutions will look like. You just need to calculate the discriminant. So the discriminant is b squared minus 4ac. Now, since it comes from the quadratic formula, you need to make sure you're in standard form, right? So in this case, we are. A is 4, b is negative 12, and c is 9. So our discriminant would be b squared, make sure you use parentheses, minus 4 times a times c. So if you want to put that right into the calculator and avoid mistakes, I don't blame you. I do the same thing. Negative 12 squared. Again, the parentheses are important there. If you didn't put the parentheses, it's going to give you a negative 144. So minus 4 parentheses 4 parentheses 9. And you got to make sure you type into the calculator correctly. Okay, so this ends up being 0. So if we had a discriminant of 0, that means we were solving with the quadratic formula and we got a 0 underneath the radical, which would mean the radical part would go away and we would be left with one rational solution. So this tells me this equation has one rational solution. Okay, let's try this again. This, again, needs to be in standard form. So 10x squared minus x is fine, but the 2 needs to subtract over to make it equal to 0. And now we see that a is 10, b is negative 1, and c should be a negative 2. So our discriminant is negative 1 squared b squared minus 4 times a, which is 10, and c, which is negative 2. So let's put that in the calculator. Calculator want to move? There we go. So we have a negative 1 squared minus 4 times 10, 10, and then negative 2. Okay, so end up with 81 this time. Let's see if I can put my calculator back. Okay, so if our discriminant was an 81, it means we would be solving with the quadratic formula. We got a positive 81 underneath the square root. Well, we're going to be able to square root that number exactly and add it or subtract it from whatever was in front and go about and get two rational solutions from that. So this positive perfect square tells me this will have two rational solutions. Okay, next one. Already in standard form, we can see a is 1, b is negative 5, and c is 3. So discriminant is going to be negative 5 squared minus 4 times 1 times 3, and 25. Jeez, I could, if you could do that in your head, awesome. If you want to use your calculator, let me just not try to screw anything up. 1 and really, and 3. So we end up with 13. So a discriminant of 13, if 13 was another radical, we can square root 13, we're just going to get that non-repeating, non-terminating decimal. It's a positive 13, so it's not going to be complex or imaginary. They're just going to be ugly solutions, so there are two irrational solutions. So this tells me this equation has two irrational solutions, two souls. All right, now the last one I'm sure you can determine based on what's left what the answer will be, but feel free to pause and give it a try. So we have a equal to 1, b equal to -2, c equal to 4. So the discriminant is -2 squared minus 4 times 1 times 4. And so we end up with, let's see, 4 minus 16 is going to be a -12. I don't have a calculator for that. All right, so if a discriminant was a -12, whether this 12 was a 12 or a 25, the fact that it's a negative means we're going to end up with the negative coming out as an I. So this tells me that this equation is going to have two, we can either say complex or imaginary solutions. Two complex or imaginary solutions. No fun abbreviations there. Okay? All right, so if you're asked to determine the number and types of solutions, you are using the discriminant. Now, if you wanted to go through all of the solving and then look at the solutions, I suppose you could, but that discriminant is going to tell you what the solutions will look like, okay? Now, on the back, instead of solving or looking at the solutions, you're going to be given the solutions, and then the task is going to be to determine the equation that produced those solutions, which could sound kind of difficult, but think about this. If 5 is a solution or -1, let me go to my scratch paper for a second here. If I said to solve x squared plus 5x plus 6 was equal to 0, right? This thing could be solved by factoring. The factors of 6 that make 5 would be 2 and 3, right? So if this factored into x plus 2 and x plus 3, then I could see that -2 would have to be a solution, and I could see that -3 would have to be a solution. Well, all we're doing now is working backwards. Now we're trying to come up with this equation that we had in the beginning, but we don't have to jump all the way back to that step. Couldn't we jump just to this step first, right? If -2 is a solution, it's because x plus 2 is a factor. Or if -3 was a solution, it's because x plus that 3 had to be a factor. And then if I could write out the factors, then we're just distributing those factors to figure out what our original equation was, okay? So a pretty simple process. If, let's say a, just some number a is a solution, well, let's just even call it a number. If a number, some random number, is a solution to our quadratic equation, then x minus that number had to be a factor of the same equation, okay? So if you had some number as a solution, then the opposite had to be in the factor. That's what negative is an opposite, right? And so you're going to take your opposites of your solutions and then plug them into factors, okay? And then it's just multiply those factors, distribute those factors to get the equation in standard form, and then make sure that it is actually an equation and not just an expression. So make sure you have this equation that's set equal to 0, otherwise what you're doing makes no sense, okay? So if 5 is a solution to this first equation, it's because x minus 5 was a factor of that equation. And if -1 was a solution, it's because x plus 1 had to be a factor, right? This is how we get a solution of 5. This is how we get a solution of 1. So now that we have our factors, we just multiply. Well, x times x, let me get rid of this. X times x is going to be an x squared. X times 1 is going to be an x. Here we get a -5x. Here we get a -5. Again, equal to 0, otherwise it's not an equation with those solutions. And then we combine our like terms. So x squared minus 4x minus 5 was the equation that produced those solutions. Not so bad, right? Okay, what if we have fractions here? Are we scared of fractions? I hope not, right? If there's a +5 here, a -5 here makes sense. Well, now there's a +2 and there's a divide by 3, right? So if there was a +2 there, that would make a -2 have to be here. Well, if there's a divide by 3, that's what the 2/3 means, right? There's division by 3. That means there had to be a times 3 in the factor, right? Think about your bottoms up process. If this came to the front of 3x plus that 2, just change the sign, and we have our factor. So this tells me that 3x minus 2 had to be a factor, right? The opposite of the plus 2 is the minus 2, and the opposite of the divide 3 is times 3. Oops, eraser. Oh my goodness, eraser. So that's that, and then if we have a negative 1/4 here, divide 4 means I need a times 4, minus 1 means I need a plus 1. So 4x plus 1 would give me a solution of negative 1/4, and this has to be equal to 0 for that to happen. So now we're going to multiply this out. Get rid of this. So 3x times 4x is going to be 12x squared. This is going to give me a positive 3x. Here I get a negative 8x, and then here I get a negative 2. We're going to combine like terms, so we end up with 12x squared minus, just kidding, minus, let's see, minus 8 and positive 3 makes minus 5x, and then minus 2 equal to 0. And there's our quadratic equation with those two solutions. Okay? Now, number 6, we were only given one solution. So now I want to go back to the front here. This is what I wanted to go back to earlier, but I wanted the timing to be right. So here's an example in this last box, this fourth box, of where we ended up with just one rational solution. Now I used the quadratic formula to solve there, but if I was given any option for solving, it's not the one I would have chosen, because this is actually factorable. 4x squared plus 4x plus 1. Let me take it to my scratch paper. 4x squared plus 4x plus 1 had one rational solution. Now, if we were to factor this, what are the factors of 4 that make 4? Factors of 4 that make 4 would be 2 and 2. Now, if I divide each of those by 4 and reduce them both, we get the same thing twice. We get a 2x plus 1 and a 2x plus 1, which means we get negative 1/2 as a solution twice. Okay, so we saw it occur only once because it's redundant to write it twice. If your quadratic equation has only one solution, it technically has two, but what's happening is the solution happens twice. So technically, the verbiage here, we would say that x equals negative 1/2 is a solution with a multiplicity of 2. I'm not so concerned that you know that just yet. We're going to talk about multiplicities and that vocabulary in a later unit, but if your quadratic equation has one solution, it's because the one solution happens twice. Okay, so it's the same solution twice. We just don't see it happening twice. So here in number 6, x equals 3 is our same solution twice. This happens twice. So it means that x minus 3 is a factor of the equation 2 times. So we have x squared minus 3x, and then plus 9. And then combining the like terms, x squared minus, wow, I'm getting really sloppy here. X squared minus 6x plus 9 is our equation. Okay, so if you're only given one solution, it's because that one solution has a multiplicity of 2. It happens 2 times, so you're going to have the same factor twice in your equation. Okay, now, number 7, I know it looks a little different, but this is saying that positive 2i is a solution and that negative 2i is a solution, right? So we can use the same process here. If 2i is a solution, we could say x minus that 2i is a factor. And if negative 2i is a solution, we could say x plus that 2i is a factor, which looks strange, but when we work this out, you're going to hopefully see an answer that makes sense. If we multiply, now these are conjugates, right? What's going to happen? Well, we're going to get an x squared here. We're going to get this 2xi, which is weird, but that's okay. This is going to cancel with a negative 2xi here. And then here, negative 2 and 2 makes negative 4. I times I would be I squared. So these go away. And if you knew that was going to happen and you wanted to skip that, that'd be fine. And all we're left with is x squared and negative 4i squared. But what do we know about I squared? Well, I squared is equal to negative 1. So really, this is just x squared plus 4 equal to 0. X squared plus 4 equal to 0. Now, does that make sense? Right? Think about this equation. If we were to solve this, what would we do? Well, we would subtract the 4 over, and then we would square root. and we'd get a plus or minus 2i, which is exactly the solutions that we came up with before. Now, if you can see that that's the equation that's going to produce those two solutions and skip all that work, you absolutely can. I just wanted to make sure that that work made sense. Get rid of this. Okay, went too many times. Okay, so there we go. And the same process will work here now. Again, if you can see what's going to produce these two answers, knock yourself out. But if you want to, pause and try it out. But we can use the same process we did before. So this is saying that 2 radical 3 is a solution, and that negative 2 radical 3 is a solution. So I can put their opposites in my factors here, and I can multiply. And these are conjugates. So I'm going to have an x squared, and I know that this 2x radical 3 and that this negative 2x radical 3 are going to cancel. So if you wanted to skip those, be my guest, welcome to do that. And then negative 2 positive 2 makes negative 4 in front of a radical 3, and 3 is 9. Okay, so these cancel, and I'm left with x squared minus 4 times radical 9 is 3, which means my equation is x squared minus 12. And again, that should make sense. If you were to solve this, you would add the 12 over, and you'd square root it, and you'd get plus or minus. When you simplify the 12, a 2 is going to come out, and a 3 is going to stay, plus or minus 2 radical 3. Okay? All right, the last one is the one where I want to show you a process that's a little different. It's more along the lines of how I might solve this U-try or number 7. So I could use the process I used on the last several. I don't know why I changed color and then didn't. Sorry, brains everywhere. I could put in x minus 1 plus radical 3i. Hold on. This is saying that 1 plus radical 3 and 1 minus radical 3 are solutions, right? I could do x minus the first one, and I could put that in a binomial, and I could do x minus the second one, and I could put that in a binomial and try to multiply those. But multiplying 3 terms times 3 terms, that's going to give me 9 terms, and I don't want to deal with that, okay? So I want to show you another approach. Should have used a bigger eraser. Another approach, okay? It's really along the same lines, just another way to look at this thing here. So why is there a positive 1 on this side of the equation? Well, if there's a positive 1 there, it started as a negative 1 on the other side of the equation. So I'm going to undo the solving here. If I subtract this 1 over, that's gone. So now I have x minus 1 on this side equal to plus or minus the square root of 3 on this side. So if I unsolve the solving, right? So why is there a plus or minus radical 3 on this side? It's because I took that square root, right? And why did I take the square root? Because there was a square. So I moved the plus 1 with a minus 1, and now I'm going to get rid of the square root by squaring both sides. So I square both sides. So that's going to give me an x minus 1 times an x minus 1 equal to, what's the square root of 3 squared? Well, it's the square root of 9, but that's just going to be 3. And so if I FOIL this out, multiply this out, I have an x squared, a negative x, another negative x, and a positive 1 still equal to 3. And now I can subtract that 3 over. If I subtract that 3 over, and I combine my like terms, I have x squared, negative 1 and negative 1 makes negative 2x's, 1 and negative 3 makes negative 2, and now it's equal to 0. And there's my equation that produced those two solutions. Okay? If that makes sense. And again, you could have used a similar approach on any of these. So it's like undoing the solving, working backwards. So you should be able to look at an equation and determine, based on the discriminant, how many solutions it will have and what those solutions will look like.